Diffusion models have fundamentally changed generative AI, but they come with a heavy tax: inference speed. To go from pure noise to a coherent image, you typically need dozens, sometimes hundreds of numerical integration steps along a stochastic or deterministic trajectory. Researchers have responded with distillation techniques to compress these paths, but most of them make a critical trade-off. They either sacrifice the stochastic nature of the sampling process, locking you into a single deterministic output, or they require heavy, teacher-based distillation pipelines that are computationally expensive to train. What if we could distill the full transition map of a diffusion process directly, preserve its probabilistic structure, and do it without a pre-trained teacher? That's exactly what Stochastic Transition-Map Distillation, or STMD, achieves. To understand why STMD matters, we need to look at how modern diffusion models actually generate data. Continuous time diffusion models frame generation as solving a reverse-time stochastic differential equation. Instead of taking tiny, incremental denoising steps, we want to learn a direct map from noise to data. This is where flow matching comes in. Flow matching approximates the drift of the underlying ode, or SDE, by learning a velocity field that transports a simple prior distribution, like a standard Gaussian, to the data distribution. The standard approach trains a neural network to match the conditional velocity between data and noise points. At inference, you still have to numerically integrate this learned ode, which is slow. To skip the integration, recent work like mean flows learns the average velocity along entire trajectories. This allows the model to take exact, finite-time steps, effectively learning to integrate the flow in one go. But here's the catch: mean flows and consistency models are built for deterministic flows. They learn a single noise-to-data mapping. In many downstream tasks, though, deterministic sampling falls short. Tasks like diffusion posterior sampling for inverse problems, energy-based fine-tuning, or even just improving alignment with user prompts, fundamentally rely on stochastic inference. You need to sample from the full transition kernel, not just the conditional mean. STMD bridges this gap by distilling the transition probabilities of the reverse SDE directly. Instead of predicting just the mean of the posterior, it learns the full conditional transition map. Let's break down the mechanics. We start with the variance-preserving SDE, which is essentially an Ornstein-Uhlenbeck process. The reverse-time SDE has a drift term that depends on the score function, which we can estimate using Tweedy's formula. But rather than training a score model, STMD parameterizes the transition density by conditioning on the original data point. Because the bridge measure between the data point and the noisy input is known in closed form for this SDE, we can bypass direct simulation of the reverse process. Instead, we build a conditional mean flow model in a latent space. This model learns to map a prior sample to a sample from the posterior distribution, conditioned on the noisy input and time. The key innovation is the training objective. STMD uses a conditional mean flow loss that minimizes the deviation between the predicted average velocity and the theoretical velocity derived from the straight line interpolant. Crucially, this objective is purely regression-based. It doesn't require a teacher model, it doesn't need bi-level optimization, and it avoids simulating and caching long trajectories during training. You just sample pairs from the forward process, compute the conditional velocity, and optimize. The stop gradient operator is applied to stabilize training by preventing backpropagation through the numerical calculation of the Jacobian vector product. And the authors prove that the gradient of this conditional objective is mathematically equivalent to the standard mean flow objective. Now, distilling a stochastic transition map without a teacher sounds powerful, but does it actually converge to the true process? The authors provide a rigorous theoretical foundation for this. They derive convergence bounds in the 2 Wasserstein distance, which measures the minimum cost of transporting probability mass from the generated distribution to the true data distribution. The main theorem shows that if the conditional mean flow error is bounded during training, the Wasserstein distance between the distilled single-step generator and the true data distribution is exponentially bounded by that error. They extend this to the conditional case, proving that the learned transition kernel converges in expectation to the true reverse SDE transition kernel. There's also a careful accounting of the approximation error introduced by using a standard Gaussian prior instead of the exact diffusion terminal distribution, bounded by a Lipschitz condition on the learned velocity field. This isn't just empirical curve fitting, it's a mathematically grounded distillation framework. Let's look at the empirical results. The framework was tested on unconditional image generation and conditional inpainting across MNIST, CIFAR10, and Celeve. For MNIST, they used a standard UNet and measured performance using the Freichit distance in a classifier latent space, since standard FID scores can be misleading on low-resolution datasets. STMD matched or beat the baseline mean flow and DDPM models while retaining full stochasticity and requiring significantly fewer function evaluations. On CIFAR10, the model generated high-quality samples with just a handful of inference steps, again without needing a pre-trained teacher. For Celeve, they scaled up to a DI-T architecture, achieving an FID of 8.28 with just 4 inference steps and 2 mean flow steps per step. They also demonstrated conditional inpainting, showing that the preserved stochastic transition structure allows the model to handle partial observations effectively, which is critical for inverse problems. STMD represents a meaningful step forward in making diffusion models both fast and probabilistically faithful. by distilling the full transition map of the reverse SDE using a teacher-free conditional mean flow. It removes the bottleneck of iterative integration while keeping the stochasticity that many advanced applications actually require. It avoids the computational overhead of teacher distillation, comes with solid Wasserstein convergence guarantees, and performs competitively across multiple datasets and architectures. As the field moves toward real-time generation and complex conditional sampling tasks, methods like STMD that preserve the underlying probabilistic structure of diffusion will become increasingly important. If you're working on fast generative models, inverse problems, or energy-based fine-tuning, this is definitely a paper worth digging into. Thanks for watching, and I'll see you in the next one.